Hi everyone, my name is Paria Gharavi. I'm an assistant professor and a new faculty in Department of Material Science and Engineering, College of Engineering and Computer Science at University of Central Florida. Today I'm talking about the wonderful world of materials through the lens of transmission electron microscopy. I'm gonna start with a quick background on myself. Actually, I'm a triple degree holder in material science and engineering. I'm coming from UPenn. I did my postdoc under the supervision of Professor Eric Stack, who is a pioneer in electron microscopy. And of course, my research interest is about all of the advanced TEM techniques, including in situ and a new one, which is called 4D S-TEM. I'm going to talk about it later. Also, thin film technology, including deposition and characterizations, specifically at interfaces for novel materials, including ferroelectrics and semiconductors. This semester, I teach design and selection of materials, but my interest is any kind of characterization techniques of materials and, of course, TEM. And in summer, I will teach structure and properties of aerospace materials. Among all of my achievements, I mentioned a couple of them here, like Best Speaker Award in the annual user meeting of Think Center for Nanotechnology at UPenn, and winning in some of the electron microscopy competitions like GL USA and USA National Nanotechnology Coordinated Infrastructure. And the most important one for myself is that the whole of my PhD was covered by a prestigious award, which was in Australia, which was called UIPA, University International Postgrad Award. And my PhD thesis was recognized for Dean's Award for Outstanding PhD Thesis back to 2019. And because of these achievements during my PhD, I was honored to be invited for the Global Talent Program by Department of Home Affairs, Immigration of Australia, and I got my permanent residency visa through the talent program. Let's start with the quick motivations about my research. Here you can see very famous pyramids in material science and engineering that you can see at each corner: structure, processing, performance, and properties of materials. And you can see characterization techniques at the center of this pyramid, which shows the important role of characterization techniques in material science and engineering. So in summary, I study advanced novel materials using electron microscopy techniques to have a better understanding of structure, process, property relationship at atomic scale. The impact of my work is in two ways. First one, a better understanding of behavior and potential application of materials. Also, to develop new technologies and materials with enhanced properties in different industries like electronics, energy, aerospace, medicine, and so on. And here I mentioned to a couple of grants. Actually, 2 days ago, we were awarded NSF-REU site, which is for research in materials for energy applications. And also, recently, Professor Kushima submitted a new proposal, NSF-MRI, for aberration-corrected TEM for research and education in quantum, semiconductor, energy, and biosciences. Also, I have my own startup funds from UCF and a couple of more grants. Before starting about my research, I'm gonna show you how we can unlock the secrets of advanced novel materials using electron microscopy. And during this one, I wanna ask you to think about your own research, think about your own materials and see that how can you unlock the secrets of your own materials using electron microscopy. For example, whenever it comes to think about the morphology or the surface topography or compositional analysis of a material, like nanoparticles or the surface of your devices, we can use electron microscopy. Or when it comes to observe anything under layer features, the things that are not on the surface and we cannot see them, we can use electron microscopy to mill apart and have a good look from the cross-section view and see the inside of materials. And of course, when it comes to fabrication, process, and synthesize, deposition of different materials, it's very important to have a good understanding from the size, thickness, and the chemical composition, the distribution of chemical composition of your thin film and other synthesizers. And this is some things that we can do using electron microscopy. You may notice that I talk too fast because there are a lot of things that I would like to talk about, but unfortunately, because of the time, I only select two main part of my research to talk about. First one is about semiconductor zinc sulfide gallium phosphide system, and also a new ferroelectric material which is called ALSCAN. And if you are interested in learning more about my other research, you can go to my publications, and please be in touch with me later if you have any question. Let's start with the first system, which is a semiconductor zinc sulfide gallium phosphide multi-layered film. And the application of this photoelectrode is to have a photoelectrochemical water splitting. And the goal is develop of a semiconductor photoelectrode for efficient solar to hydrogen conversion. And here, we propose that by increasing the number of interfaces, we can increase the photocurrent density. And of course, we can improve photocatalytic activity by interface engineering. But when it comes to interface engineering, it means that the mechanisms, we need to find the mechanisms at each interface. So at each interface, you can see a huge network of defects, including twins and stacking faults that act as trapping centers. Also, they help for interdiffusion and making a new unstable material, which has a better efficiency compared to material A and B. And the second system is about a new ferroelectric material, or ALSCAN, which I worked when I was at UPenn. And you can see that using electron microscopy, first of all, we can have a good check through our system to see different layers, the order, and if we have any kind of dead layer or oxide layer. For example, here you can see the replacement of nitrogen atoms by oxygen in around 4 nanometer layer, which affect the properties. Also, we can check the chemical composition and see that, for example, we have homogeneous distribution of aluminum and scandium. Diffraction patterns gives us great information about the crystallography of samples. And also for the S-TEM technique, which is the main part of my interest, is employed to measure the average spacing between atoms and gives us great information about the distribution of strain through the system. For example, for this specific thin films, we can see that we have a significant increase in the out-of-plane component, around 9%, and also around 5% in the in-plane lattice parameters, which is directly related to the properties, ferroelectric properties of this material. But let's talk about my future plan at UCF. Is that I would like to have one of the leading groups in 4D S-TEM studies of novel and unexplored materials, like some of the semiconductors and ferroelectrics. I've already started collaboration with some of the faculties through MSE, physics departments, Creole, and try to put them in different categories. However, we all know that there are some overlaps, and I really enjoy it, and I'm looking forward to collaborate with even more faculties and more departments. My 5-year plan is to, first of all, synthesize and deposition of epitaxial film, and development of a new design for a better understanding of their structural and their properties in different applications, specifically optics, electronics, and energy storage. Also, characterization of them using the instruments and the facilities that we have at UCF. So we have 3 proposals. First of all, development of new ferroelectric materials like ALSCAN, and have a good understanding of structure property relationship for them. the second one is focused on the 4D S-TEM technique specifically to see how the strain is distributed through the system. I proposed some different projects for my future PhD and master students, and the significance of this proposal is to understanding the origins of fundamental properties in novel materials. And the last one is in situ electrical biasing TEM, which is super interesting because it helps us to investigate the intermediate process of domain switching under electrical biasing. And the most important slide, which is the last one, is how to enhance collaborations. This is my plan, that how can I do my sample fabrications, the sample prep, the XRD, the ferroelectric testing, optics and photonics, and 4D S-TEM and other electron microscopy techniques, and maybe other simulations, modeling AI that I don't have any idea. And I love to work with people who are working in these topics. Thank you so much. At the end, I would like to take this opportunity to acknowledge the support and encouragement I received from my supervisor, colleagues, students, and mentors. Also NSF and Think Center for Nanotechnology, SRC, DARPA, TAFEN, and of course UCF. Thank you so much.